The goals of the snake robot gait sonification project were to collect snake robot movement data, transform the data into audio in a process called sonification, and compare the audio results from different snake robot gaits. Before covering more project details, I will describe the various snake gaits and the motivation for snake robot data sonification. Snakes are very adaptable. They are able to navigate many different terrains, such as rocks, sand, tree branches, narrow tunnels, and water. Researchers have studied snakes to understand and mimic snake locomotion. Dr. Shigeo Hirose developed the first snake-inspired robot in 1972. Snake robot designs and uses have expanded since. Due to their ability for adaptive motion, snake robots are well suited for search and rescue assistance after natural disasters or emergencies, inspections in dangerous settings such as underwater pipelines, and space exploration. There are 4 key snake locomotion types, also referred to as gaits. The most common is lateral undulation, or serpentine motion, which the entire snake moves by propelling forward. The rectilinear gait is one in which the snake's skin moves relative to its skeleton to slide forward. With the concertina gait, the snake alternates between pulling its body into bends and then straightening out. This gait could be used to move inside tunnels or along tree branches. The side winding gait involves the snake bending from side to side and lifting off the ground, and this is used in case of contact with a slippery surface. Shown here are the 4 snake gaits and robot designs to mimic each of those gaits. However, there are some limitations with snake robot data. One is interpretation of the joint data. With sonification, the data is transformed to music. Sonification of data could help in robotics education, calibration, such as auditory perception of how tuning parameters affects performance, and understanding movement of a snake robot when it is out of sight, such as potentially climbing a tree in a search and rescue mission or in space exploration. It could also provide information on restrictions for the snake robot, such as obstacles and narrow spaces. It is a different method of representing robot motion if visual data is limited. This was the motivation for my project, to model snake robot gaits and create sonification clips. To model snake robot gaits, Coppelia Sim software was used. Coppelia Sim is a robotic simulation environment with preloaded common robot models and obstacle objects. The preloaded robot movements can be modified by changing the Lua VREP scripts. One of the preloaded snake robots was the ACM R5 robot with fins and passive wheels. I used the ACM R5 robot for simulating serpentine and rectilinear gaits. However, due to the design of joints with a 45-degree range, the concertina and sidewinding gaits were not able to be simulated. After the simulation data was collected, I created the sonification code with the following steps. First, identifying the data parameters to use, then identifying the musical parameters to change, and finally, adjusting the mapping, range, and polarity for the parameters. For serpentine motion, this is the equation for the target angle for the ith joint of the robot. There are several data parameters in the equation: the maximum amplitude, the frequency, phase shift, offset, and a scaling function to vary the amplitude. Shown here is an example mapping and polarity between data parameters and musical parameters, such as amplitude, frequency, phase shift, offset, and scaling function mapped to the pitch, tempo, rhythm, timbre, and volume. I experimented with different snake robot gaits and different sonification mappings. In the Coppelia sim script, I updated the actuation for a simple serpentine movement in one plane. Then I saved and exported the target joint position to a CSV file. This was used as a baseline to try out some different mappings. First, I tried varying the tempo based on the frequency. However, the tempo needed to remain at 60 beats per minute in order to be timed to the simulation correctly. Next, I mapped the position to the pitch, with the minimum and maximum peaks corresponding to the lowest and highest notes of a scale. I also tried two polarities. First, I tried the higher position value mapped to a lower volume. Then, I tried the higher position value mapped to a higher volume. I determined the higher volume was more intuitive. Shown here are some experiments with different serpentine gaits. I changed the amplitude, the frequency, and the offset. I also simulated a couple different rectilinear gaits by modifying the amplitude and the phase shift. In addition, I simulated an eel type of gait similar to the serpentine, but with a scaling factor applied to each of the joints. Then, I tried two different sonification methods. The first was generating music based off of the data. The second was modifying existing music. With the music generation approach, I tried different trials to adjust the scale, note duration, and tempo and volume for different gaits such as serpentine, rectilinear, and eel. For music modification, I changed the pitch shift, the tempo, and the volume depending on the type of gait. There are some lessons learned with this project. The first was related to the rectilinear gait simulation with the ACM R5 robot. There are two cases shown. However, the simulation was very sensitive to larger changes in parameters that limited collecting more cases. Most of the time, changes in the parameters resulted in the simulation not running. Another limitation was with the volume values used for mapping. The expected range was from 0 to 255. However, the audio clip output cutoff was more limited, so I had to modify the range from 40 to 120. And although the amplitude was mapped to volume, it was not very noticeable. I tried to increase the separation of minimum and maximum volume values for different gaits by applying an exponential function. Here are some potential next steps. First, is experiments with more complex gaits and obstacles, such as gaits with horizontal and vertical position data, like a swimming robot, and also adding obstacles to the environment and then creating sonification based on the output joint data. Also, the sonification code could be tested with physical robot data to check its robustness, since there may be noise in the data that would require adjustment in the sonification mapping or the thresholds. And last, it would be helpful to distribute surveys for feedback on adjusting the sonifications to be more intuitive. Thank you, and thank you to Dr. Mohammadi for advising this semester.